Okay, so the purpose of this lesson is to learn how to simplify radical expressions. Now, that word radical indicates anything that has a square root symbol or a root symbol like this. That's a radical. So when we talk about simplifying radical expressions, we're talking about being able to simplify expressions that have those in it. So the purpose of today's lesson is to teach you guys how to simplify expressions with radicals by evaluating their factors. Now, we know that a root symbol represents, or when it's a plain root symbol, like a normal one like this, it represents finding the square root of a number. So if I put something like 25 underneath that radical, that means the square root of 25. And if you know square roots, then you know the square root of 25 is 5. You'd have learned this in 8th grade. So the reason the square root of 25 is 5 is because 5 times 5 is what gives us 25. A square root tells us to figure out what you could multiply by itself twice in order to get the number under the radical. So 5 times 5 is 25, which is why the square root of 25 is 5. If you had something like square root of 16, well, 4 times 4 is 16. So the square root of 16 is 4. So the purpose of our lesson today is to look at that, but not to evaluate perfect numbers like 16 and 25, but to learn what to do in situations where you have something that doesn't have an integer that multiplies to give it. Something like, for example, the square root of 20. You can't multiply anything by itself, not a whole number anyway, by itself, to get 20. So if you calculated the square root of 20 in your calculator, you would get some crazy number, like 4-point crazy stuff. So we're going to look at how we can simplify that into whole numbers, but still leave behind part of what's in the radical. So this is not a super difficult lesson, especially if you're pretty good at multiplication. But we'll kind of walk through this slowly and make sure we all have a basic understanding of it. So to be able to simplify a radical expression, we've got to consider perfect squares. So we simplify radical expressions or expressions inside of a radical only when one of the factors is a perfect square. So a factor, remember, is a number that you can multiply by itself. Or a number you can multiply, not by itself, but a number you can multiply to get a number. So if you could multiply a number to get, or two numbers to get the number inside the radical, and one of those numbers you can multiply is a perfect square, then you're able to simplify that radical. So what we basically do in order to do that is we break that number that's inside of the radical into two integer factors. Now, integer factors is important. They have to be whole numbers. Integer is like a whole number. It could be positive or negative, but a whole number. So integer factors. One that's perfect and one that is not. Once you do that, so you break that into two factors. So let's do an example of this as we work this problem. If I asked you to find, let's say, the square root of, I want to use one that I know I don't use later on in this. Let's go with 60. So the first thing I've got to do is figure out two numbers I could multiply to get 60, one of which is a perfect square. And we're going to go to the next slide in a minute and do a cheat sheet of perfect squares. But what I know is that I can multiply 4 times 15 to get 60, and 4 is a perfect square. Now, I know I could multiply 2 times 30 and get 60, but neither of those is a perfect square. I know I could multiply 5 times 4. Nope, not 5 times 4. 5 times 12, but neither of those is a perfect square. So I've got to pick two numbers that are perfect squares in order to do this. So I'm going to use 4 and 15. And once I've done that, I'm going to find the square root of the one that's perfect, and that's going to turn it into a whole number. And I'm going to leave the one that's not perfect under the radical. All right, sorry, y'all got caught up in some people coming in my classroom. Anyway, so once you get that broken into two factors, one that's perfect and one that's not, We take the one that's perfect, so this 4 is the one that's a perfect square. We change it into its actual square root. The square root of 4 is 2. So I change that to 2. I leave the part that's not perfect, so the 15 that's not a perfect square stays square root 15. And we write it as 2 radical 15. And you might say, well, that doesn't look any simpler than the square root of 60. It really doesn't look any better, but if you were doing some multiplication or division with it, that would give you something that you could actually work with and make a simpler answer, which is kind of the purpose of what we're doing there. So we'll go and look at some more examples of this in a second, and hopefully it will kind of make a little bit more sense to you. So let's look at, first of all, making a cheat sheet of perfect squares, because if you don't have a basic knowledge of perfect squares, then this is going to be hard for you. You're going to have a really hard time with what to skip. So first thing we want to do is think about what are those perfect squares that we're going to look for. So perfect squares, remember, are numbers that you get when you multiply an integer by itself. So, for example, 1 squared is equal to 1 times 1. That means 1 is a perfect square. So 2 squared, 2 times 2 is 4. That makes 4 a perfect square. 3 squared is 9. 9's a perfect square. Now, when I taught 8th grade, I had my kids memorize these because it made it easier when you get to algebra to do this kind of stuff. But if you don't have these kind of committed to memory, you need to get them kind of stuck in your head somewhere, because you're going to need a basic idea of what these numbers are, what numbers you're looking for as you get ready to simplify these things. So we're going to make a list of them all the way to 15 squared. That's obviously not all of them. You can keep going forever. Oops, sorry, that should say 10 squared. Now, you can figure these out without this list, of course, and if you don't have a good knowledge of them, you can test them out till you get ones that work, but that just takes a long time and makes these problems harder to solve. So the quicker you can get them kind of committed to memory, the easier these problems will be for you. And then we'll do a lot with squares when we're factoring, when we get into algebra next semester. So kind of having a good knowledge of them at that point will be useful. All right, and then 15 squared is 225. Actually, I think we'll go on to 16. I don't actually know 18 and 19 and 20 squared, but we'll put them on our list anyway. It might come up 324. It's 361. And 20 squared will be 400. All right, so that's going to give you just kind of a list to reference. Now, the numbers that you're looking for from this list to be factors of what's inside your radical are the numbers that are the perfect squares. So you're looking for the things that fall on this side. Now, what they become once you simplify them is the whole number from the other side. But you're looking for these numbers to be the factors. And you want to go with the biggest of these numbers you can. So, like, if 4 will go into the number, but 16 will also, you would want to use 16, even though both are on our list. Because 16 will pull more out of it than the 4 would. So let's look at how we kind of do this. All right, so here we have our first example is radical 12. So the first thing I want to think about with this is what 2 numbers could you multiply to get 12? So 2 numbers I can multiply to get 12, one of which is on my list of perfect squares, are 4 and 3. Now there are other numbers I can multiply, because I could do 1 times 12, don't write this down, or 2 times 6, or 4 times 3. Those are all ways I can get 12. But the only of these numbers that are perfect squares is the 1, which doesn't help us, and the 4. So I'm going to use this 4 times 3 because that's the biggest perfect square option that I have. So Once I do that and I break that 12 into 4 and 3, I'm going to call this root 4 times root 3. Now, I take the part of that that is perfect. So we already know the 4 is the part that is the perfect square. I'm going to take that and I'm going to break it back into its whole number form. So the square root of 4 is 2, and I get 2 square root 3. So that becomes 2 because it's a perfect square and it simplifies to 2. 3 is not perfect. We leave it radical 3. All right, let's look at 75. So 75, if I'm thinking about my list of perfect squares from the slide before this, and I want to go with the biggest one that I know will go into 75, 25 times 3 would give me 75, and 25 is on my list. So I'm going to go with 25 and 3. $25 is the one that's perfect. So it's the one that I'm going to simplify. 25 square root is 5. So this simplifies to 5 root 3. Now you can check and make sure you've simplified this correctly by typing in square root of 75 and getting your crazy decimal, and then typing in 5 square root 3 and getting your crazy decimal, and making sure those two things match. If they do in your calculator, then you know you've done this correctly. If they don't, then you might want to go back and look and see what happened. All right, let's look at 48. So ways we can multiply to get 48. Now, you might look at that and you say 4 times 12, and you're absolutely right. 4 times 12 will give you 48. But there's actually a bigger option that works here. So think about, you can do 1 times 48. You could do 2 times 24. You don't have to write this down, by the way. You can do 3 times 16, or you can do 4 times 12, or 6 times 8. Those are all the ways that you can multiply and get 48. So when I think about all those different ways, and I look at all these numbers, the biggest number out of all these numbers that is a perfect square is 16. So I'm going to use 16 and 3 to break this down, because I need to choose the one that gives me the biggest perfect square option. So the square root of 16 times the square root of 3 is how I'm going to break that up. If you used 4 and 12, because 4 is also a perfect square, you get a simplified answer, but it's not fully simplified because 12 could break down again because another 4 could come out of it. You need to choose the option that will simplify completely your radical. So the square root of 16 is 4, and the square root of 3 stays square root 3. So our answer is 4 root 3. All right, and the last one on this slide is root 20. So ways I can multiply to get 20 are 1 and 20, which 1 is the perfect square. 2 and 10, neither of those is perfect. 3 will not work. 4 and 5, 4 is perfect. So that's my best option. Root 4 times root 5. 4 is a perfect square. So I go with 2 root 5. So this is not super difficult if you're pretty good at multiplying. If you're struggling with multiplying, it may help you to go through and make those lists of factors that you can do. So like on this one with the 20, if you needed to, you could have gone through and wrote down 1 times 20, 2 times 10. Tested 3 out, realized it didn't work. Tested 4, worked it with 5. And that would be the end. When you hit that, you'd be repeating 5 again at that point. And then from there, you could pick up that this is your best choice. So if you're struggling with that part, like how do you know what 2 numbers to go with? Just make a list of things that work until you don't have any more factors to use, and then pick your biggest one from that list. So take a minute on your own, pause the video, take a minute, and try the ones on the next slide. You'll try these, break them down into 2 numbers, one of which is perfect, just like that, and then find the square root of the one that's perfect and leave the rest of it alone. So take a few minutes, pause this video, try that, and then when you're done, come back and see if you got correct answers on them all. All right, so take a look at these answers that I got. And if you missed any of them, go ahead and make corrections to whatever it is that you missed. But for the first one, I broke it into 25 and 5, and that 25 became a 5, so I got 5 root 5. The second one I broke into 36 and 2. 36 became 6, because 6 times 6 is 36. So I got 6 square root 2. 18 breaks into 9 and 2. 9 was perfect, so it became a 3, 3 root 2. And 28 broke into 4 and 7. 4 was perfect, so it became a 2, 2 square root of 7. All right. Hopefully you got all those correct. Now with 72, you might have done 9 and 8 instead. And if you did that, I see where you would have thought that would be a good option because 9 is perfect. But 8 is made up of 4 and 2, which means you could have pulled another 2 from that, using that 4. And so it would not have been finished yet. You could have simplified it further. So 36 and 2 was the better option. 36 was the biggest perfect square that would evenly come out of 72. All right, let's now go look at some involving variables. So what happens if you have a radical expression that also has variables underneath it? And I'm talking about like if you're looking at something like square root of x to the 4th. That's what I'm talking about with a radical expression with variables. You can rationalize a variable too. Rationalize means to simplify the radical. So if you're looking at something like this with a variable, here's what we need to understand. When you're finding the square root of something, you're basically finding how you can evenly split what's in there into 2 equal groups. Not dividing by 2, but 2 groups that you would multiply together that would equal whatever's under that radical. So if I want to take x to the 4th and think about what would multiply by itself to give that, well, x to the 4th really means x times x times x times x. So to split these 4 x's into 2 equal groups that could multiply, I would have to make 2 groups of 2 each. So the square root of x to the 4th is just x squared. If I did the same thing, and you don't have to write this down, I just want you to kind of understand where this is coming from. If I did the same thing with x to the 6th, and I wanted you to find the square root of that, we would have to consider if we had 6 x's, and I broke them into 2 groups that could multiply by themselves to get that, I would have to evenly break it into groups of 3 and 3. So x to the 3rd is the square root of x to the 6th power. So basically what you can see from that is that whatever your exponent is, when you find the square root of it, it cuts it in half. 4 cuts it in half to become 2. 6 cuts in half to become 3. Now what if you had a situation of like x to the 5th? And you wanted to find its square root. You'd have x times x times x times x times x. The only way to make equal groups with this would be to have 2 groups of 2 and have 1 left over. So this becomes x squared and 1x still inside the radical. So you're able to pull out half of, or 4 of those x's into x squared and leave 1 of those x's behind. And that is where this gets kind of tricky. Most people understand it when they're even, but they have a hard time when it's odd. So here's what I want you to try to remember from all that. If the variable has an even exponent, all you have to do is half it and move it out. So that's that x to the 4th. And you half it and it becomes x squared. But if it has an odd exponent, remember odd numbers are like 1, 3, 5, 7, 9, 11, 13, 15, odd numbers. You're going to half it and move it out of the radical. But you're also going to leave a variable to the power of 1 inside the radical. This represents the remainder, because you would always have a remainder of 1 letter left if you had an odd number. Now, when I taught this in first block today, they felt like it made more sense, instead of saying to take something like x to the 5th, half the 5 and get x to the 2.5, and you take 2 out and put 1 left in. They thought it made more sense to think about this as x to the 4th times x to the 1st, because then they could remember that x to the 4th would be x squared and x to the 1st would be 1. It doesn't matter to me which way you think of it, because it's really the same thing. But if it's helpful to you to do that, break it into 1 even and 1 by itself, and then break the even 1 in half, That's perfectly fine. It's really the same thing that I'm saying when I say you can take this, half of 5 is 2.5, put the 2 outside and leave the 1 that's left inside. It's really all the same kind of thing. So it doesn't matter to me which way you work with that. Let's look at some examples of this. So on this side, we've got some whole numbers that we're going to have to break, and we've got some variables that we're going to have to break. So we're going to kind of work this with dealing with the numbers just like we did on the last slide, and then dealing with the letters just like we just did on those notes. So if I'm looking at 512, and I want to think about what I can break 512 into, one of which is perfect and one of which is not. 512 will break into 256, which is on my list, and 2. So this is perfect. I know that. Now, k squared is already perfect because it's even. Even exponents are automatically perfect squares. So that means that the 256 and the k squared can both be evaluated, but the radical 2 will not be able to be. It is not perfect. So my answer is going to have a radical 2 in it. The square root of 256 is 16. The square root of k squared is k. So this all becomes 16k square root 2. It's a little bit tricky to look at, but that's what we want to do with that. We want to break it into perfect squares and then find a way to make our exponent perfect also. So there's one with the 80. So 80 is not perfect, but I can break it into numbers that are. So I know that 1 times 80 is 1 is perfect, but 80 is not. 2 times 40, neither of those is perfect. 80 is not divisible by 3. It is divisible by 4. 4 times 20. 4 is perfect, so that might work. It's also divisible by 5. Five times 16. 16 is bigger than 4, so 16 is a better number. It is not divisible by 6. It's not divisible by 7. It is divisible by 8. 8 and 10. It's not divisible by 9. So that's all my list right there. And so 16 and 5 are the 2 numbers I want to use. So I'm going to break this into root 16 and root 5. And then that p to the third is not perfect the way it is, but I can break it into p to the second, which is perfect, and another p, because 2 and 1 would make 3. And so if I do that, what I end up with is this is perfect and this is perfect, and those 2 are not. So I'm going to break those down. Square root of 16 is 4. Square root of p squared is p. And everything that's left goes back under the radical. So 5 and p are under the radical together. All right, let's check on 200, m to the 4th n. 200 is pretty easy to work with because we know 100 is a perfect square, and 100 times 2 would make 200. So root of 100 times root of 2 is how I'm going to break that up. Now, oh, that's not an eraser, just kidding. Okay. Now, the m to the 4th, it's even, so it's perfect. The n is not. Only even ones are perfect. So this is perfect and this is perfect, which means I'll break those down. The square root of 2 and the square root of n are not. They'll stay under the radical in my answer. So I know my answer is going to have a radical 2n with it. But on the outside, the square root of 100 is 10. The square root of m to the 4th is m squared. All right, now let's look at this last one. We have radical 64, m to the 3rd, n to the 3rd. Now, when I look at the 64 part of that, 64 is a perfect square. So it can stay all by itself. It doesn't have to break into 2. Now, the m to the 3rd and the n to the 3rd are not perfect. So I'm going to break them into m to the 2nd and m. because m to the second is perfect, and n to the second, and n, because n to the second is perfect. So from all of these factors that I've broken down here, 64 is perfect, m squared is perfect, and n squared is perfect. And so my m and my n by themselves are going to stay in the radical. But I'm going to break these other things down. The square root of 64 is 8, because 8 times 8 is 64. The square root of m squared is just m. The square root of n squared is just n. And we're getting those square roots from these variables. I haven't been explaining that very well. We're getting the square roots from the ones that we said are perfect just by halving the exponent. Half of 2 is 1. Half of 2 here is 1. Over here, half of 4 was 2. Up here, half of this 2 gave me 1 on the outside. Half of this 2 gave me 1 on the outside here. So the ones that you know are even, the ones that are perfect, you're halving them to move them out. All right, take a minute, or take a few minutes to pause the video and try the 4 on the next slide. And then when you're done, come back and check and see if you were right. You should be working the ones on this slide with your video paused. When you're done, you come back and check and see if you are correct. All right, so take a look at this and see if you got the same thing that I did. And I'll kind of walk through them real quick in case you missed any of it. If you got them all right, you can stop the video right here because you were done. But if you missed a few, take a look and see what I did and see if you can correct what you did. So for 75, I broke that into 25 times 3. And then for x squared and y, I just broke those down into this one was already perfect. This one was already not. There was no need to split any of those up. And so then from there, I recognized that 25 and x squared were both perfect. So I found the square root of those and got 5 and x. And then the stuff that was not perfect stayed under the radical. For 125, I did the same thing. I broke it into 25 times 5. 25 was perfect, so I changed it into 5. N by itself under the radical was not perfect, so it stayed in the radical with the 5 that was also not perfect. For 28, x to the third, y to the third, I broke 28 into 4 and 7. 4 was perfect. I broke x to the third into an x squared and an x because this would be perfect and this would not. And I broke y to the third into a y squared and y because this would be perfect and this would not. And so then I square rooted everything that was perfect. Square root of 4 was 2. Square root of x squared and y squared were x and y. And then everything that was left over stayed in the radical. And then with 100, v to the third, 100 was already perfect, so I left it. But v to the third had to break into v squared and v. So the square root of 100 was 10. The square root of v squared was v. And I left the other v that was not perfect in the radical. All right, you are done. You can go ahead and submit those notes. Thank you. Y'all have a beautiful day.